Thank you for the introduction. So first, I'd like to thank all the sponsors and organizer, including as well Aurélien and Mathias Schubert for financially supporting this event. The talk will start with an introduction of microstructure in the heart, and then I will explain how diffusion MRI works and some of the clinical applications. So when you think about how the heart is shaped, you need to understand that it's made of myocytes, and those myocytes are actually where is my laser? Stuck into this muscular lacunae, and they stuck together and they form myofibers. And this endomysial collagen act as a honeycomb to preserve the myocytes and fiber from overstretching. And they also preserve the anisotropy of the fibers, and they help in the diastolic recall of the fibers. When you think about how the heart's contracting, you actually have the myofibers stuck together with the perimysial collagen to form sheetlets, and sheetlets are separated by another type of collagens. And when the heart is contracting, actually, you have the sarcomere that are contracting, but they only contribute to 15% of the myocardial thickening. Most of the thickening is actually the 40% that you see an increasing of the wall thickness is actually from the sheetlets sliding onto each other. And those sheetlets, you can actually see them as well on the orange image. And you have actually two types of population of sheetlets, which are orthogonal at midwall, and you have these kind of gaps between them to allow them to slide onto each other. Actually, there is a publication showing how this sheetlets configuration works and how the fiber are stuck together with the sheetlets. With diffusion tensor imaging, you can, as you know, you can track the fiber orientations, but you can also, with the second and third eigenvector, you can estimate the sheet angle, and they show there is a linear correlation between the wall thickness and this sheet angle. So you have this helical orientation with the contraction like this, and then you have the sheetlets sliding into each other. And most of the, as I say, most of the thickening is actually from those sheetlets sliding onto each other. This animation is quite oversimplified. If we actually look at really high resolution imaging, this is 3.5 microns, which was done with X-ray FS imaging. It's really complex. You really have here it's the LV posterior, you have the LV insertion, which with really compact fibers. Then you have, as I say, those cleavage planes. And actually, when you look at those cleavage planes, they actually correspond to the myocardial perfusions. And here are delineated sheetlets and roughly the angulation of sheetlets. Those sheetlets, there's the gap you saw earlier, actually, it's not empty. It's full of the vasculature and collagens and veins and arteries. So if you think about the sheetlets starting parallel and then sliding onto each other, it actually affects how the perfusion works, because you kind of changed how the flow behaves. So you have this section, but because of different pressure, so actually change the perfusion during this study. And if you look at only the arteries, you can see that in those segments, the perfusion is actually different. You have hypervascularization of the septum, and some of the oxygen doesn't have this. The reason is that it's kind of surprising, because when you look at the heart contracting, most of the contraction is uniform, but actually the microstructure is different. And the perfusion actually highlight this, because the perfusion is also related to the microstructure organization. In the RV, it's not really it's hypoperfused. The reason is because most of the RV contraction is allowed by the LV contraction, and this is what we call the Barrier effect. because the RV insert into the LV. And as I say, some of the segments, they're quite different from each other. You start with really compact fibers from the RV with no sheetlets, and then you have very small sheetlets, which are orthogonal mid-wall, and then at the endocardium, a really large cleavage plane and sheetlets with really large vascularization. This is kind of quite a contrast compared to the septum. In the septum, you have a lot of cleavage plane and sheetlets, so a lot of perfusion as well. And if you look at the epicardium, it's kind of look like the RV structure where you don't have any, you have a very small cleavage plane, so not much perfusion, and it's really compact fibers. Here it's more a highlight of this really cut between the epicardial layers and endocardial layers. And so if you look at some of the late ganglion enhancement imaging, you can really see this clear cut here in a B2, which is the one here between the RV, which is infarct, and then you have this clear cut at the epicardial layer and endocardial layer, and that's because of the difference of structure you have. The other spots you might see in some of the edgy imaging, it's also because of the way they do the procedure. There is a reloading of the reconfiguration or modeling of the loads onto some specific segment that are not designed to handle to cope with this new demand. So how do we get the fiber and sheetlet orientation? So typically, this is done with a spin-echo sequence where you have diffusion gradients on both sides of the 180 pulse. And so when you apply gradients, you dephase the spin, and you expect that when you apply another gradients, the same thing, you should recover all the signal. The issue is that some of the spins actually diffusing, and so they don't refocus the echo, and so you lose signal. So one important to understand is that when you measure diffusion, you actually measure a signal loss. So if you do this for at least 6 direction, you can obtain a tensor with eigenvectors, and basically the water diffuses the fastest along the fiber directions, and so it's anisotropic, and you can then differentiate different type of tissue. Basically, in terms of sequence acquisition, as I said, this spin-echo sequence with CPI, and mostly we're trying to acquire what we call the sweet spot, where the strain is minimized, and it's a little bit before the systolic end of the diastole, and systolic. You can actually use trickery to trigger delays to acquire systole and diastole. And we use motion compensation gradients of the moment of second order to minimize the effect of acceleration and velocity. Once you have the tensor, you can project the eigenvectors to obtain different angles, and these angles correspond to the fiber and sheet angle I talked earlier. The transverse angle is basically how much the fiber deviate and tilt inward toward the endocardium. When you do imaging, it's really important to keep in mind the contrast between what you acquire and what's actually the scale of what you're measuring. So this is a 3.5 microns, and our voxel is 3x3x8 typically. And then you put a tensor, you do this for all your voxels, and then you have this tractography. This is really, it's really important to understand that this kind of tractography, it's useful from academic point of view, where you can roughly understand how the fiber configuration works, but it doesn't have any clinical values because there's a lot of interpolation, and it doesn't really underline the complexity of the microstructure at the macro scales. But it at least gives you an overview of how it looks. Some clinical application, however, can be useful. Here it's some of the examples. Literally with leg investments, there's no distinction between remote or border zones. And if you use diffusion tensor and different metrics, you can actually able to differentiate those different zones and better characterize the impact. In another study, they occlude some arteries and then they reperfuse it, and then they compare between T1 and T2 maps with diffusion, and how when they quantify the reperfusion and assess the heart, they show a greater differences using apparent diffusion coefficient, which is the mean diffusivity compared to T1 and T2 maps. Regarding the sheetlet dynamics, as I say, you have the sheetlets sliding onto each other, and you can quantify these sheet angles, and they demonstrate that some pathology, for example, in hypertrophic cardiomyopathy, the sheetlet has kind of stuck systole, while in dilated cardiomyopathy, they kind of stuck diastole. So there's a lack of sheetlet motion and dynamics. Then they try to retrieve those sheetlet dynamics, and they were able to quantify with the sheet angle and see the correlation and see they could retrieve some ejection fraction. Some of the work I did during my PhD, so this is some pictures from someone else from the 90s, where they did a dissection of the trachea fallow and with RV dilatation. And what's really interesting to see is that some of the fibers here with dilated RV, it's really the remodeling really affect how the fibers change, and so the cardiac output as well. And you can see as well that because of the dilatation, you have two apex as well, and so it also affects the stress on the heart. One of the reasons I did some DTI in tetrahedral fallow specimens, and actually show that it's kind of like a balloon. You place a girdle on a balloon, and because of the preponderance of circumferential fibers in those specimens in patients with such surgery of fallow, while healthy patients don't have such configuration. And if you use DTA as well, looking at the ventricular septal defect, you can actually quantify how the fibers change through the wall thickness, and show that they actually lack longitudinal fibers, so it decreases the cardiac the longitudinal shortening, and therefore the cardiac output. As I probably mentioned, when they do surgery and congenital heart disease, mostly they try to change the growth anatomy for the patient to be able to survive, but they don't really consider the sheetlets and fiber configurations. So when they change the anatomy, you change the loading onto some segments, and those segments are not necessarily designed to handle such stress and strain. So you end up with specific spots, like a LV insertion. And what we are testing is to account for the structure and to assess the impact of the remodeling, and as I said, the redistribution of stress and strain. So with LG, we can only image the failure of the surgical repair. What we need to do is investigate the structural remodeling to better understand the consequences of surgery, which could provide better predictable outcome. Shortly about this is just a point of view I have. You often see these graphs, the way we segment the heart is very Cartesian. We can see that some of the segments are affected and some not. I think we need to rethink about how we segment the heart, because Most likely it's because the way the fiber are all affected, and so all the signals might actually be linked because of the fiber configurations. So in conclusion, is this just a personal point of view? There have been a lot of studies on T1 and T2 maps over the last 20 years, and now we have a new matrix which can quantify and consider the macrostructure and dynamics. The macrostructure is also affect the electrical pathway because it follows the least resistance, and that's why you have this helicoidal orientation. Affect the perfusion, as I say, can regulate the distribution of stress and strain, and a relationship with the collagen, as well as the dynamic of the heart. So better characterizing this matrix will help us to better understand biomechanics to identify markers of predicting outcome in various patient disease. Thank you.